double integrals and volume. Well, you've already been introduced to the double integral from section 14.1. We use that as the foundation. If you take the double integral and then you apply in the integrand a function, in particularly a height function, thus we're able to deduce the volume of a solid. So without that height function, then all you resort to is just looking for some iterated double integral, which is what we looked at before. So if we take in the x, y, z space, if we take some solid here that's colored in blue, z is set to give the surface. The r here, the region, is set to be what's happening in terms of the image of the surface or the solid in the xy plane. So that region is important. Green, in Green's theorem, says that to investigate what happens on the surface or even in the solid is to investigate what's actually happening in the region. And so he focuses on the region, then he defines it in a certain way to connect it with the surface. So whatever happens in the surface or in the solid is actually also going on in the XY plane. So we want to be able to look at this particular surface and dissect in it small cubes, and then use the Riemann sum to find the volume of the individual cubes, add them all up, and take a limit, and we get here the summation of all these cubes, which thusly gives us the volume for the solid. So we take this surface, we look at what happens in the XY plane. This is this region R. We slice it up into rectangular tiers downstairs. We call them partitions, very similar to the partition that we talked about for the Riemann sum. But for that partition for the Riemann sum back in Calculus 1, we only talked about the X partition. We looked at the neighborhood about X. Here we look at the neighborhood about XY. So we take these squares or rectangles. Above each rectangle, there exists here some tubing, some function f. We call that the height, right? So we have the base. If I could find this base area, the base area basically is the region R. Take that base area, multiply it times the height of each one of these rectangles. And what that gives us is these cubes that stick out. Some stick out above the surface, some are protruding below. But taking the limit and with the right partition, taking the limit, we can actually approximate the actual volume itself. So here this volume is said to be the limit of the summation of all of these cubes. So for each one of these cubes, we have a height, we have its base. The height is this f x sub I, y sub I, and then its base for each one would be some delta, the change of the area, the base area. Here the precise meaning here of this so-called volume. It's said that for every epsilon positive, there exists a delta. It's the same argument in Calculus 1 for the limit. There exists some positive delta, some suitable delta, such that the absolute value of the limit, if it does exist, minus this summation. What's the summation? That's the integral. And here it becomes the double integral. Why is it a double integral? Because this is a function of x and y. So I need to be able to have an integral that focuses on x and then an integral that focuses on y. So we have this absolute value. What's the absolute value? It's just the measure. It's just the measure, the length between some proposed limit with respect to its this double integral. Is less than some epsilon. What is epsilon? Typically, epsilon is very close to zero. It's very small. The smaller epsilon means that you force this summation to get close and close to the true limit. Right? Again, those partitions is what's happening with x and y here within the region. Well, here's the theory. We just kind of deduced the definition for the so-called double integral if f is defined on a closed bounded region R in the xy plane. So f is defined on the region, what's happening down below. Then this so-called double integral of f over R, this double integral is given here by the double integral of f of x, y, dA. dA again is this delta A, this delta A sub I. Here, what makes this double integral exist, hopefully, is based on the limit as the partitions, as those squares or those rectangles down below in the xy plane get smaller and smaller. So when we shrink them, that kind of weeds out for us those rectangles that protrude over the surface and then some rectangles that are below that surface, right? So taking this limit, making this guy these partitions very small, we send those to zero. We say that this double integral exists, and it's true if the limit exists. If the limit does not exist, we say that f is not integrable. But if the limit exists, we say that f is integrable. Fabini's theorem basically says the same thing that we looked at in 14.1 of how we define the region: vertically simple, horizontally simple. That's all that was. Let me show you. So in a nutshell, what we've done already in 14.1, we do the same thing in 14.2. We just give it a name, right? Remember the running worm, but that's Chief Geronimo, but he called himself Running Worm, right? And I think the other guy, he said his name was Yellow Hair or something, but then at the end he said he was Wild Bill. So we're just claiming now Chief Geronimo and Wild Bill. So Fabini's theorem, what makes it his theorem is that what we talked about in 14.1, he was one of the mathematicians in the earliest sense to give a proof that the double integral does exist. Basically what he did was he found that limit of the double integral. And there were some others who had actually preceded him, but he published his before them. So men like Leonardo Euler is believed to have deduced this a little bit before Fabini's, but Fabini took the credit because he had his information published before some of the other mathematicians. Let f be a continuous function on some plane region R. F is defined for number one, basically the so-called vertically simple. R is defined by the lower and upper bound for x, a, and b, and lower and upper bound for y, g sub 1 and g sub 2. where G1 and G2 are continuous on the closed interval, AB. And so we have exactly what we talked about yesterday from 14.1. Exact same thing. And then number two, if it's horizontally simple, the same exact thing we talked about yesterday, but here we just put the formal name to it. So this is the same as we talked about vertically simple. And then down here, horizontally simple. So if for the vertically simple, we want to if we have two functions, but here he calls them G sub 1 and G sub 2, and they're bounded by vertical lines A and B. Or for the horizontally simple, here we have two horizontal lines, and then we have functions there. So y equal to D and y equal to C. And then this is H sub 1 and H sub 2. And the region that you want to find the so-called double integral, or the volume with respect to, is contained in here. Well, let's see. Let's see if we can do just that. Let's take the first problem. Find the double integral. Here, the region is defined as a rectangle with vertices. Let's look and see. I put it up here. So we're at the origin, 0, 0, and then 0, 5. Just say it's there. And then 3, 5. We got 3, 0 is there. And then 3, 5 is here. So you want to find the double integral of this region of what happens to x, y as it is exists above this rectangle. Right? So if you look at that, x goes from 0 to 3. Right? So our region you can write as x goes from 0 to 3, and then y goes from 0 to 5. So we have a double integral of x, y. If I use dy dx, the vertically simple, then the y goes from 0 to 5. That's first to be integrated, and the x goes from 0 to 3. And if you change that up to write that as dx dy, then you just change the positions of 0, 3, and 0, 5. Right? So we integrate first with respect to y. So we have the integral from 0 to 3. This is x, y squared over 2. Y is evaluated from 0 to 5. And then we have dx. We evaluate the y at the 5. There, that gives us 5 squared divided by 2, or just 25 over 2. Just a number. Put that in the front of the integral from 0 to 3 of x dx. Then we integrate with respect to x. This is 25 over 2 times x squared over 2, and x is evaluated from 0 to 3. So that gives us 25 times 9 all over 4 And that just gives us, was that 225 over 4? Again, there's no change from yesterday from 14.1. Right? And that's the good thing. Any questions there? Okay. Yes, sir. Okay. Thank you. Okay. Here's a really cool one. Find the double integral of this guy. This is a trapezoid bounded by y equal to x, y equal to 2x, x equal to 1, x equal to 2. So we have y equal to x, and we have y equal to 2x, to something like that. And then x equal to 1, x equal to 2. So it's this trapezoid. That becomes the region in the xy plane. So this is y equal to x, the lower function. This is y equal to 2x, the upper function. So you can write the region as r is equal to, x is bounded from 1 to 2. 1 less than or equal to x less than or equal to 2. And then y is bounded from x below to 2x above. So we have this double integral here, 1 to 2 for x, and then x to 2x for y, and this is y over x squared plus y squared. And since we're dealing with y first, that's that inner integral, so this is dy dx. And you definitely want that because this y in the numerator and that y squared down in our denominator can help us use a u du substitution. If we let u equal to our denominator, we can pick up the numerator. So here let u equal to x squared plus y squared. Remember, we're integrating first with respect to y. So this implies that du is 2y dy. Here, integrating with respect to y makes that x a constant or coefficient. And so to represent our numerator, y dy, then that just becomes 1/2 times du. So this implies that 1/2 du is equal to y dy. Now they have this problem in Weber-Sign, and he says, set up the integral both ways. Set it up vertically simple, set it up horizontally simple, and then he says you solve for the most convenient way. Well, the most convenient way is this way right here, this vertically simple. And I had a student to email me and ask questions about, setting this guy up for the horizontally simple. And I wanted to tell him, why bother? It's very hinderous to cook that up. And so I shared it with him, and I said, who really cares? Just, my thing is, you have a double integral, and sometimes, like the horizontal simple is just too far out there. Don't even deal with that. The vertically simple is easy. Work it that way. Now, sometimes the horizontally simple may be easier. Well, if that's easier, work it like that. So you may run into that, and if you do, just let me know, and I can share some insights on that with you. So here, this is the integral from 1 to 2. Then this is the integral from x to 2x, and we're replacing the y's with the u's. And so here, this is the 1/2 sitting there. And then this x squared plus y squared is u, so that's downstairs. So I have a u here. And then upstairs, I have this 1/2 du. I'm just going to put a 1 and say du there. So this is 1/2 times the integral from 1 to 2. Well, the integral of du over u is just the natural log of u. So this is the natural log of the absolute value of u. That's the u is evaluated from x to 2x, but don't forget that u is x squared plus y squared. I think we have a dx sitting on the outside. So I have that 1/2 there, the integral from 1 to 2, the natural log. I better go back and put u in there, x squared plus y squared. And it's the u going from x to 2x. So this is 1/2 times the integral from 1 to 2, the natural log. Here we evaluate y at 2x. We get x squared plus 2x to be squared, and then minus the natural log of x squared plus x squared. So let's simplify that. Boy, I tell you, problems make you sweat. So I think the next problem is for you, so I won't have to sweat so much when we get to the next problem. We'll let you do some sweating. Thank the Lord is cool in here. This is the natural log of the absolute value. That's x squared plus 4x squared, so that becomes 5x squared, minus the natural log of the absolute value. And I'm going to drop the absolute values because these guys are being squared. So this is 2x squared dx. So now we use a property of the natural logs, that the natural log, the difference of the natural logs is equal to the natural log of the quotient. So this is the natural log of 5x squared over 2x squared dx. Right? You remember that one? So this is 1/2 times the integral from 1 to 2. Here, that's just the natural log of 5 over 2. That's just a number. It's just a number. We get excited when we see a number. I forget this movie that I saw with my son when EJ was about 6 years old. I mean, it was really cool. What's this guy? Andrew Banderas, I think that's his name. Antonio Banderas. And I think it was called the Eighth Men, the Ninth Men. They were like mercenaries, and this tribe somewhere out in the Middle East had hired them to kill these like alien type people. They were living in caves, and it was this lady in this cave. I guess she was like a queen bee, and she was giving birth to all these weird people, these guys, and they were just going through the community, just terrorizing people. It comes off of it's the Middle East version of Beowulf. You know, Beowulf comes from the Viking type, folklore, but it's the same story, but over from the Middle East. Where Beowulf comes out at night, he terrorizes, communities and that type of thing. And so Antonio Banderas, he's hired as he's like the ninth guy with this expedition of mercenaries. And these guys were tough, man. It was like Hulk Hogan type guys and stuff. And so Antonio Banderas, he's like the youngest, smallest type dude, but he's very religious. He's a Muslim. He's very devout, and it was really cool how he portrays this role. And this one town gets terrorized by these strange beasts. People are afraid, and they're coming out and they're slashing people. Whatever. And so these mighty mercenaries, they come to the rescue. They're fighting, but they're kind of afraid too, because these are like subhuman type creatures, right? So they're fighting. Like, what is this? They're cutting this guy, and green gobbly blood going everywhere. And so Antonio Banderas, he's praying like, God, what are these things? Are these things are they gods or something, or what? Because I'm afraid. And then I think he killed one or two, and he realized. He said, "Oh, So I said, he said, they're not aliens. They're humans. He said, they're humans. And when he said that, he got strength within himself. He told the other guys, he says, nothing to be afraid. They're men just like us. You know, if you're fighting a god, of course you'll be afraid. But he said, they're men just like us. Man, yeah, y'all know what I'm talking about? I don't know. The ninth man or something, you know? Oh, man. But anyway, I got excited because all this stuff just boiled down to the natural log of 5/2. It's just a number, just like me, and I can deal with that. It's just a number, man. You know, man. I'm like, yes, I can master that now. You know, it's not bigger than me. It's a number. Oh man, you could probably Google it, but it's a really good movie. My son, when he was a kid, man, he really enjoyed it. Joshua knows EJ, man. It's a small world. Joshua lives right across the street from my in-laws, man. So, and he went to Sparkman, and you knew EJ at Sparkman. EJ said he knew you. I said, man, it's a small world. Yep. Okay, so let's go. This is 1/2. I can pull that number out. This is the natural log of 5/2 times the integral from 1 to 2 dx. Integrate with respect to x. This is 1/2 the natural log of 5/2. Just put that in parentheses to distinguish that from this x being evaluated from 1 to 2. Get 1/2 times the natural log 5/2. And then this is times x evaluated at 2 is 2 minus x evaluated at 1 is 1. So we just get 2 times 1. It's just 1 times everything else that we have left. And that's that. And Donnie, when I looked at your paper, it looked like you were thinking that for that previous problem. Right, right. That's right. Exactly. Yes, sir. I kind of read you. I kind of thought that's what you were thinking. Yes, sir. Yes, sir. That previous problem didn't have a y or an x in the numerator, so you couldn't use a u-du substitution. So it made it a little bit more trickier. Yes, sir. You had to pull up that trig identity. Yes, sir. Yep. Well, try your hands at this one right here. Find the double integral. That region that's defined R is some parabola being intersected by a line. So you want to try to draw that out or see what's above, what's below, find the points of intersection. So graph the region to determine what function is above and which function is below, and then secondly, set the equations equal to determine the points of intersection. What did you get for your points of intersection? 0 and 1? Yes, good. What's your lower function for y? 4 minus x. So the upper function is 4 minus x squared. Yes. Yep. Negative 6 over 5. No? Because, no, you're not finding the volume. Look at what's given. This is the double integral of negative 2y dA. Right? So that's not a height. It just said find the double integral. Right? We'll get to some where they say find the volume. Right? Yes, sir. The algebra gets very tricky. Are you experiencing that? Did anybody get negative 6 over 5? Let's examine it. And I apologize because I wrote on my paper here that I'll work this one and you'll work the next one. Because I mean, it's a good exercise problem, don't get me wrong, but I don't want you to take too much time and then I'll come back and, work it out. So let's do this. I'll work this one through, and the next one I won't work. I'll just give the answer and see if you can get that one. The next one is a whole lot quicker to get, I promise you. And I know Mr. Donnie doesn't like my promises. So let's see. So you have the integral from 0 to 1, and then the integral from 4 minus x to 4 minus x squared. And this is negative 2y dy dx. Does everybody have that? Okay, good. And I think for these double and triple integrals, setting it up is the challenge. If you can get that, that's the first hurdle. Just set it up correctly. The neat thing is that, later on in life, we got Maple and Mathematica to solve the rest of it for us, if you get stuck with something. So, but just, or Card Academy and that type of thing. So let's see. This is the integral from 0 to 1. We integrate with respect to y. We get negative y squared. Negative 2y squared divided by 2 is just negative y squared. It goes from 4 minus x to 4 minus x squared. Okay, don't act up on me now. Let's put the negative out in front, the integral from 0 to 1. This is 4 minus x squared to be squared minus 4 minus x to be squared dx negative integral on. This is what the lady told the man when she left him. She said she needed more space, and I need more space here. Nah, that's a bad joke, right? Need more space. I don't know what that means, so. Oh, okay. Let's get back. I think the math is a little bit better, so. Oh, man. We'll leave it at that. Thank you, Mr. Tuggle. So, so we're going to square this guy. This is, which FOIL that out as 16 minus 8x squared plus x to the fourth minus, I'm going to FOIL this out and then affect that with the negative for each term. So this is 16. This would be minus, but times the minus is positive. That's 8x. And then this would be positive, but this becomes minus because of that negative there. X to the second. This is dx. So the 16s cancel out. Integral from 0 to 1. Negative sitting out in the front. So this is minus 9x squared plus x to the fourth, and then that's plus 8x dx, and then we can hide that negative. So this is 9x squared minus x to the fourth minus 8x dx. So now we integrate. This is just algebra or calculus, if you will. This is 9x to the third divided by 3. That just becomes 9x to the third minus x to the fifth over 5 minus 8x to the second divided by 2 is just 4x squared. Evaluate that from 0 to 1. We get 3 minus 1/5 minus 4. So we get negative 1 minus 1 over 5, excuse me. It gives us negative 6 over 5. Okay. Again, it's not the volume that we're looking for. Yeah, that'll throw you off. So what did you get? Positive 6 over 5? Oh, yeah. Oh, okay. Yeah. Yeah, it happens, man. Just one little detour throw you off. Yes, sir. Did you get 0 and 1? You set the two equations equal? Did you do that for Yes, sir. You did. Okay. See, number 2 says set the equations equal to determine the points of intersection. Right. This implies that x equal to 0 and x equal to 1. Okay. All right. You try this one. And when you work that, let's see if you come out to this. I'll put the answer here. This is 1/4 times the natural log of 17. We get it? Some say yes, some say no. John, you got it? Joshua? Yes, sir. Mm-hmm. Yes. Yep. That makes it easier if you use for that second integral that u du substitution. You have some x in the numerator, and then you get that 1 plus x squared in your denominator. Yep. Does your setup look like that? Okay. Good. So you integrate with respect to y for 1/2 y squared over 1 plus x squared. The y goes from 0 to the square root of x. So this gives you 1/2 times the integral from 0 to 4 of an x over 1 plus x squared dx. So you let, yes sir, you got it. Good man, good. So you let the u equal to 1 plus x squared, du is 2x dx. So you have 1/2 and also another 1/2, so you have 1/4 times the natural log of 1 plus x squared. The x goes from 0 to 4. So when you plug in x to equal to 4, you get 16 plus 1, the natural log of 17. and it's 1/4 times that. And then the other one is 1/4 times the natural log of 1. That's just 0. So it's just 1/4 times the natural log of 17. Is everybody okay now? Okay. All right. This is a very interesting one. Find the double integral. Here the region is a sector of a circle and the first quadrant bounded by y equal to the square root of 25 minus x squared, and then some line. So this line here is, think about this as negative 4y is equal to negative 3x. So we get y is equal to 3 over 4 times x. So I have this circle, part of the circle. So let's say this is 3 over 4x, and this is for the square root of 25 minus x squared. So if I go to the here, this line, if I let x equal to 4, then y is equal to 3. Right? X is 0, y is 0. For the circle, if x is 0, y is 5. If x is 3, you get 25 minus 9, you get the square root of 16, I get 4. If x is 4, we get 3 over there. So the first quadrant just puts us with this quarter of the circle with radius 5. This line has, we got coordinates there, 0, 0, and then 4, 3. And they share that point, 4, 3. And then it says also include y equal to 0. Well, y equal to 0 is the x-axis. So this is our region here. So it's bounded by y equal to 0. It's bounded by that line, 3/4 x. And then it's bounded by the curve there. So we get y equal to 0, y equal to the square root of 25 minus x squared, and then y equal to 3/4 x. So it's bounded on all of its sides. Right? Now, I think you see the point of intersection, but to just prove it, we set both of these equations equal. So that's the 3 over 4 x is equal to the square root of 25 minus x squared. Square both sides, so we get 9x squared over 16 is equal to 25 minus x squared. So if we get the x's on the same side, we have x squared plus 9x squared over 16 is equal to 25. This gives us 25x squared over 16 is equal to 25. Divide both sides by 25, multiply both sides by 16, and we get x squared is equal to 16. X is equal to 4. If x is equal to 4, then y is equal to 3 over 4 times 4, and we get 3. Well, we knew that because we had it there, right? So we see here that x is bounded below at this corner here, 0, and then it's bounded, it goes up to 4. And then the y goes from 0 need to break that into parts and show you. When x goes from 0 to 4, the below function for y is 0, but the above graph is just 3 over 4 times x. And x then goes from 4 to 5. And when x goes from 4 to 5, the below function for y is 0. Then the above function for y is that curve, the square root of 25 minus x squared. We call this piecewise function. Right? So let's see how that looks. I have two regions. Call that region 1 and region 2. I can't see that. So region 1 is x goes from 0 to 4 and y goes from 0 to 3 over 4 x. And then region 2 goes from x goes from 4 to 5, and then y goes from 0 to the square root of 25 minus x squared. Now, so this problem here is this double integral of x. And this is from 0 to 4. This is from 0 to 3 over 4 x. And this is dy dx plus the integral from 4 to 5, the integral from 0 to the square root of 25 minus x squared. That's the x dy dx. And this was vertically simple. Right? I told you that it may be easier sometimes to compute it horizontally simple. Let's look at that. This is vertically simple here. The horizontally simple says, can you find two horizontal lines up and above, and then can you find a function to the left and a function to the right? Well, the function to the left is that line, and the function to the right is that curve. Right? That may be easier and quicker to get. Both ways will give you the same answer. So let's look at that from the so-called horizontally simple. Let me just put the graph back up here. As a matter of fact, for this one, you don't even have to break it up into parts like that. We have y equal to the square root of 25 minus x squared. Y is 3 over 4 times x. And then y equal to 0. Now, if we did that, let's see, this point here, again, was 4 comma 3. So this is 4 there. So y is bounded below by 0 and bounded above by the 4. X is bounded to the left by this line and is bounded to the right by this curve. But you got to watch how you write that based on Fabini's. So the below function, just take the inverse. This becomes 4/3 y is less than or equal to x is less than or equal to the square root of 25 minus y squared. You see that? This is horizontally simple. Go back and look at how the horizontally simple was defined. 2 horizontal lines, C to D, and then below is h sub 1 of y, a function of y. And above, h sub 2 of y, a function of y. And then dx, dy for the horizontally simple. That's why we had to write this function here as 4/3 y, right? Just took y equal to 3/4 x, solved for x, right? So x equals to 4 over 3 y. That's all we did there. The same thing for the y equal to the square root of 25 minus x squared. Just solve for x in terms of y. Okay. So I work it using the horizontally simple. This is the double integral. We're going from 0, I think that was 4. Yes. Make sure it's 4. It's 3. X is 4, y is 3. Doggone it. Let's get that right. That'll mess us up. X goes from 0 to 4, but the y goes from 0 to 3. And then below, we said that we had 4/3 y, and above the square root of 25 minus y squared. And I think this guy was given as is x. So this is x dx dy for horizontally simple. So the integral from 0 to 3, this becomes x squared over 2, evaluated from 4/3 y to the square root of 25 minus y squared, and dy over there. That x squared helps us with that radical. That x squared is going to help us with that radical. Let's say this is 1/2 times the integral from 0 to 3. Here, I evaluate these terms at x squared. So this is the square root 25 minus x squared. To be squared, the radical goes away. Minus 4 over 3 times y to be squared. Uh-oh, that's a y right there. So you get 1/2 times the integral from 0 to 3, 25 minus y squared minus 16 y squared over 9 dy. Well, I see some common terms there. So this is 25 minus 25 y squared over 9. dy. Integrate. We have 25y minus 25y to the third, all over 3 times 9 is 27. The y is evaluated from 0 to 3. 25, well, 1/2 times 25 times 3 minus 25 times 27 over 27. So we get 1/2 times 75 minus 25. We get 50 over 2, or just 25. Okay. Now, if you want to, you can work that using that vertically simple. You have 2 double integrals, you come up with the same thing. Yeah. So sometimes in web assignment here say set them up both ways, but you work the most convenient one, the easiest one. And sometimes it may be easier to do the horizontally simple. My go-to one is the vertically simple, but if it looks more challenging, I'll resort to the other one. Okay. Now, 3 more problems. These next 3 problems focuses on the volume. Focus on the volume. We hadn't talked about the volume. We just looked at basically double iterated integrals. So let's see how that works out. Here, find the volume. The first octant simply means that x is positive, y is positive, and z is positive. So we talk about the volume, we're talking about x, y, and z now. So the first octant is the first quadrant, and then everything above it for z, positive. So if we look at all of our boundaries for the region, I have x going from 0 to 1, y 0 because x is in the first quadrant, so the smallest thing that it can be is 0. It goes to 1. Y goes from 0 to x cubed, and then z goes from 0, it tells me that, to xy. Later on, a couple more sections, we'll talk about the triple integral. Let me put that here for you quickly and give it to you. We talk about the volume in terms of the triple integral. Let me show you how it's related here. If you have the boundaries for x, y, and z, you get it. The volume will be from 0 to 1, the integral from 0 to x cubed, then the integral from 0 to xy. So 0 to xy is the boundary for z, that's dz. The boundaries from 0 to x cubed is y, so that's dy. And then the boundaries from 0 to 1 is dx. But for this problem, I digress. Oh boy. Not that digress, but hit the wrong button. I digress to say this, that this is the integral from 0 to 1, the integral from 0 to x cubed, and then the height function is that z equal to xy. So this is just xy dy dx. Integrate first with respect to y. You have here the integral from 0 to 1. This is xy squared over 2. Y is evaluated from 0 to x cubed dx. So here we have a 1/2 sitting there, integral from 0 to 1. This is x times x to the third to be squared dx. Evaluate at 0, then the integrand goes out. So this is 1/2 times the integral from 0 to 1. Power raised to a power, you multiply the power, so we get x to the 6th times x to the 1st is x to the 7th dx. Integrate, this is 1/2 times x to the 8th over 8. Evaluate that from 0 to 1. So we just get 1/2 times 1 over 8, or 1/16. That's the volume. Okay. give you one to do. It's easy. Yes, sir. Please remind me to put this back on because yesterday I did. Yoda. I love the old Star Wars. Yoda, Jabba the Hutt, those guys. The old Star Wars. Let's see what you got. Let's see. How does 32 over 3 sound? What do you say, Joshua? All right. Everybody else? 32 over 3? What do you mean? Like, like what? I mean, help. As a group, oh man, wouldn't that be grand? Yeah, man. Yeah, that's not a bad idea, man. Yeah. I never forget about 10 years ago, man, I had a real cool class and man, and they would be, my class was like around lunchtime, so they'd get hungry, I get hungry, so they said, we ought to, bring some bologna and stuff and bring a little portable grill and, they did that one day, man. They brought some bologna and some hot dogs and some bread and stuff. We went outside, man, and barbecued and yep. Yeah, man. That was cool stuff. Wow. Did everybody get 32 over 3? Okay. You still working, Joshua? Okay. Just give you just another minute on that. I won't be able to get to it today. Yeah. Um, I think the test can still be on the 12th. Just on Thursday, I have to double up and cover 14.3 and the next section. I think I'm skipping. No, because look, guys, we still got chapter 15 to cover, and that's two tests on that. So, and what will end up happening, I don't want to get there, is that I just have to rush through everything, and that's not good on the digestive system. You start hiccuping again, right, man? So, uh,
I thought it was a day ahead.
hmm?
I thought it was a day ahead.
Well, I'm saying, but if we get thrown off,
Oh.
it's a little bit easier for the online classes because I kind of say, hey, test
It's
here.
your fault.
Yeah, but when I'm teaching, so it's, and so online you can kind of watch those videos every day and kind of move on. But here I'm just stuck with Monday, Tuesday, and Thursday. So, um,
Better be ahead of them time.
that's right.
Any hiccups that way.
No hiccups, man. Did you get it, Joshua? 32. Okay. Yeah, Thursday I need to cover 14.3. I skip 14.4 and then we do 14.5. And then Monday we can do 14.6, 14.7. And then Tuesday review, I will not cover 14.8. So I think we should be still good. So as long as one day I cover 2 sections. So what I may have to do is for that day is limit the problem times that you all work in class so I can kind of get through it and to cover both. So you have this double integral. The height is x squared dy dx. Y goes from 0 to 4. X goes from 0 to 2. No. Now you can if you want to. I just put that up there on the board. We hadn't gotten to that yet. That's like a few sections later. I'm sorry. Yeah. But you can still use it and you still get the same thing, right? Yeah, so if you use a triple integral, it would be 0 to 2, 0 to 4, and then that third integral would be from 0 to x squared dz dy dx.
Oh, you still end up with the same.
You get the same thing. Yeah.
Oh, because now we got the same thing after evaluated it.
Right. So that definition for the triple integral for the volume is some triple integral over the surface or the solid, if you will, of dz dy dx, and you can change that order if you want to. But here, for the double integral, it's the double integral over the region of some height, f of x, y, let's say dy dx, or just dA, right? Then, yes, sir. Pardon me? Yes, sir. It's equal to z.
So we can't have us say like z equals 5 to our, z is the high 5.
Yes, sir. Z is that f of xy.
X, Y is our region.
Yes, sir. Xy is on the surface, and then f or z puts you up above that, right? So you can calculate the volume that way. Did you get it, Joshua? So this is the integral from 0 to 2. This will be our last problem because we only have 5 minutes. And there's another problem on there for you to do, but just leave that for you. It'll be online. This becomes x squared times y. Y is evaluated from 0 to 4 dx. So this is just 4 times the integral from 0 to 2 x squared dx. This is 4 times x to the third over 3, evaluated from 0 to 2. This is 4 times 2 to the third over 3, 32 over 3. You thought of, huh? Pardon me? All righty. You can take a look at the next one. What does the first octant mean again? X, Y, and Z are positive. Yep. Oops. Let's put the answer up there.